Okay, I think we'll get started. So today we're in a bit of a transition period between the classical mechanics that we've been studying and the quantum mechanics that we're going to need in order to understand how atoms work in any kind of way that's going to be useful to chemistry. So, as I mentioned at the beginning of this series, we are not putting quantum mechanics in these three, or at least the formal study of quantum mechanics. It's going to come up, it's going to be talked about, but the formal, rigorous understanding of quantum mechanics is going to be coming later in the curriculum. And even that's going to be layered. We're going to take sort of an intermediate approach and then a more advanced approach and then maybe even a more and more advanced approach to quantum mechanics as you progress through the curriculum. But by the same token, we can't ignore atoms and molecules in this first class. So we're going to talk about atoms at the level of general chemistry. So we'll introduce the results of quantum mechanics in the upcoming lectures, and that will allow us to talk about atoms and bonding and so on. So we're going to keep it at that level, but we do need to transition away from the classical mechanics for a little bit. Now we'll come back to that for sure, the remainder of the series. All right, so today specifically, we're going to talk about the Bohr model, which is a halfway step between the classical solar system model that we talked about last lecture and then the full-blown quantum mechanics that we'll see the results of in the next lecture and a couple of lectures after that. All right, well, to set the background, at the turn of the last century, so 1900, so around that time, it was thought that physics was essentially completely solved, and the job of physicists was simply to work out more elaborate problems to better understand the universe. But things rapidly changed as technology developed. We were able to probe deeper into the atomic level, so we were starting to see things that were smaller and smaller and smaller. We were starting to know what the structure of the atom was, that electrons existed, and there were nuclei and protons and neutrons. And we were able to extend out into the cosmos and see much greater distances. So we were expanding the realm of physics that we were able to probe with our instruments. And what we saw was things that did not match the classical theory. And in particular, a number of things, even more than listed here, but the two-slit experiment, how materials behave in terms of their heat capacity as we start to approach absolute zero. So we were able to probe colder and colder temperatures. Something called the ultraviolet catastrophe. These things we won't talk about. We'll get to them in due time as we progress through the curriculum and go on to our more advanced courses. But the key that we'll talk about today is the simple fact that hydrogen is stable. So we used the solar system model last time. We didn't talk about this last time, and we'll talk about it today. That system is not stable, and we'll see why in a moment. So these were some of the things that happened at the turn of the last century. Then there was a period where we were trying to patch the theory, classical theory, to match some of these new ideas. And the Bohr model, which is what we'll be talking about today, is one of those examples of a patch. Now, in the 1920s, the development of an entirely new theory finally arose, and that was quantum theory. And that was developed in the mid-1920s by Schrödinger, taking more of a differential equations approach, and Heisenberg taking more of a matrix or linear algebra approach. It was Dirac who very shortly after that showed that these two, although seemingly vastly different theories, one based on differential equations, one based on linear algebra, were actually the same thing, just different descriptions, different representations of the same thing. So he unified these two theories. He also did the important job of reconciling, to some degree, quantum mechanics with relativity, Einstein's theory of relativity, specifically special relativity. So he developed relativistic quantum mechanics. And one of the most triumphant things that came out of that was that an electron, he was able to describe spin of an electron. So we know electrons have this spin that we just are going to just have to tack on with the Schrodinger and the Heisenberg initial formalizations, but appears specifically in relativistic quantum mechanics. The other thing quite amazing was the prediction of anti-electrons or antimatter in general, which had not been observed. But then, of course, we now know certainly there is the existence of antimatter. We've even harnessed it in medicine in PET scans, so positron emission tomography scans. So certainly a bold prediction that came true. So all this started to and then continues to have the community of scientists gain confidence in quantum theory. Now, we do know that that's not going to be, that isn't the final theory. And one of the reasons for that is that there isn't a satisfactory quantum theory of gravity. So there isn't one theory that unifies all the forces that we see in nature and has one coherent story. So there's definitely there's more physics to be done. But in terms of chemistry, quantum mechanics, and specifically non-relativistic quantum mechanics, so the first that was invented by Schrodinger and Heisenberg, will cover all of chemistry. There's some minor exceptions in the lanthanide and actinides where you have 4 electrons in the 4f shell, where there is some relativistic effects that take place. But essentially, non-relativistic quantum mechanics covers it all. And so as we move through our curriculum here as physical chemists, the central focus in terms of quantum mechanics will be on non-relativistic quantum mechanics. But certainly, as physical chemists, we're interested in everything. And so we will see some of the more advanced quantum theories, relativistic quantum mechanics, quantum field theory, which is our most sophisticated theory to date, and even some relativity will sneak in there. But in terms of the core chemistry, quantum mechanics is what we'll be looking at. Now, as I mentioned, we will just see the results of that in the upcoming days, specifically how it pertains to hydrogen, and then the other atoms, and then on to molecules. Okay, that's a long bit of introduction to this transition period. So let's step back to last time. We looked at the solar system model. We did some calculations. We got some numbers. We put in actual constants of nature and could say some things about the energy of the solar system model. I was able to get the ionization energy and so on. But there's one thing we need to talk about yet, and that is if we have the electron orbiting like a planet, the nucleus like a sun, there is although the math is exactly the same as for a gravitational system, so the functional form of Coulomb's law and the functional form of Newton's theory of gravity are identical. Just the constants are different. And of course, gravity is a much weaker force than electrostatic forces. But we would expect, perhaps, that the solar system model would be a very good model. But there's an important difference for the electrostatic case versus the gravity case. In the electrostatic case, as this electron moves on its orbit, at one particular spot, it will be oriented in this direction. So we're going to have a negative charge and a positive charge separated by a distance. And we will come to see that as something called a dipole. And we will look very carefully at dipoles, even starting in this course. But suffice it now, a dipole is simply a separation of charge over a small distance. So when the electron is here in this part of the orbit, then the dipole is pointing in this direction. Now, 1/2 a cycle later, so 1/2 of a cycle, the dipole is pointing downward. downward. And so as this electron encircles the nucleus, the dipole is oscillating up and down. And again, I keep saying we've got to wait and be patient, but down the line we will take a course on electrodynamics, and we will discover that an oscillating dipole, as this is doing, must emit radiation, electromagnetic radiation, or light. So when this system emits light, and the light will be emitted at a frequency equal to this oscillating dipole, as you might expect, light, you got to have some energy to have light, and so the light will carry away energy from this system. So unlike the solar system model, with the Earth going around the sun, which is a stable orbit, the loss of energy due to the radiation causes this to be an unstable orbit. And the system will drain energy and eventually collapse to the nucleus. Now, we might say, okay, that may be happening. And so we have the Big Bang, the universe cools enough to start forming hydrogen. And this is happening, but it's just happening very slowly. So maybe this collapse is 10 times the age of the universe, and we're just all shrinking a little. All of our atoms are shrinking just a little bit. Well, it turns out when you run the numbers, and we won't actually run the numbers, but when we actually calculate this, we discover that, one discovers that this happens exceedingly rapidly. So shortly after the Big Bang, hydrogen forms. Shortly after that, the electron would collapse to the nucleus. We wouldn't have hydrogen as we know it. We wouldn't have molecules as we know it, and we wouldn't be talking about why hydrogen is stable. So that's the issue with the solar system model. And it's an unavoidable issue. If we say classical mechanics is right, that means Newton's laws are right, Maxwell's theory of, Maxwell's equations for electrodynamics are right, then hydrogen must be unstable, and it must be rapidly unstable enough that we wouldn't be here at all. Okay, so that's a problem, right? That's a problem, and we have to patch up this theory at the least. Typically, you don't want to just throw away a very powerful and successful theory like classical mechanics and classical electrodynamics. So you want to maybe patch it up. You say, well, okay, electrons, maybe they're not quite like planets. Maybe this isn't quite a solar system model. And that's what Bohr did. And the premise here is that we say hydrogen does not collapse, right? So we're going to start with that. And then we're going to take another experimental clue, and that is the hydrogen's spectrum, electromagnetic spectrum. So when you excite hydrogen, it gives off light, and at the time we were capable of measuring that light and measuring its frequencies or its wavelengths. And it turns out that the spectrum gives off very specific wavelengths. It's not a continuous spectrum like an incandescent light bulb in one of the old light bulbs before LEDs and other fluorescent light bulbs. An incandescent light bulb will give off just a broad spectrum. Every color of the rainbow is there. But for hydrogen, that's not the case. Only certain frequencies are there. So with the premise that hydrogen is stable and that we must be seeing discrete frequencies, not every frequency, then let's see if we can come up with a model. And the idea here is that there are special orbits for hydrogen. So there are only certain orbits that the electron can exist in. We can't exist in every orbit that would occur as we spiral to the center. If that's the case, we can label these, we can count these up to infinity, so n1, n2, n equals 3, all the way up to n equals infinity. And as an electron is in one orbit, it can transition to another orbit by either gaining energy and going to a higher orbit or losing energy and going to a lower orbit. When it loses energy, for example, to here or to here, then it gives off light. And it gives off light at a frequency, it gives off light at an energy that is equal to that difference in energy from those two orbits. So that would be a discrete value. Now, we have not talked about light yet. We certainly will. If we know the energy of the light, we know the frequency or we know the wavelength. That's fixed. So we would match what experimentally is observed, that hydrogen has these discrete line spectra. And so with that, with the values similar to what we calculated last time with the solar system model, Bohr was able to create a model that is sort of this solar system, but with special orbits, and do some calculations and match the spectral lines. And also the easiest calculation to do is, well, what if we take an electron that's in its lowest orbit, its lowest energy orbit, and pop it all the way off so that we create an ion? Well, that's the ionization energy, the energy to create the ion, the H+ ion. And so what are we doing? Kind of a trick question here, but we're going from state 1 to state infinity. So n equals infinity. So let's see if we can calculate that. Well, with doing calculations similar to what we did for the solar system model, Bohr was able to show that the energy of any of these levels is some value. The value happens to be 2.18 times 10 to the minus 19 joules. More typically, we work in electron volts when we're talking about single atoms. So that is equal to 13.6 eV. And it's equal to 1 Rydberg. In fact, the Rydberg is kind of defined such that that's the value there. So we could either say 1 Rydberg, we could say 13.6 eV, or the ugly number of 2.18 times 10 to the minus 19 joules. And the number here, the orbit number. And the orbit number, also called a quantum number, is proportional here as 1 over the quantum number squared. So this formula, it's a very, very simple formula, gives us the ability to calculate this ionization energy. We're saying final n value is infinity, so we'll call that E infinity. And the initial n value is E1, is 1. So then we'd have E1. So we would have E infinity minus E1. Let's plug infinity in here. Now, yes, it's undefined, but we think about it physically. What is it? It's just a very, 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 very large n. And so we have minus a Rydberg over infinity. So this goes to 0. And then we have minus a minus Rydberg. Oops, so that's a positive. Minus a minus Rydberg over 1 squared. And so that's 1 Rydberg. So the Bohr model would predict an ionization energy of 13.6 eV. Well, you do the experiment, it's 13.6 eV. So it gets the ionization just right. Furthermore, as I mentioned, it gets the spectral right. How would we calculate any given transition? Well, we would just say the change in energy from J to K, where J could be any value, any integer. K could be any integer. Final minus initial. And so we'll get minus the Rydberg and then subtracting the inverse square of the quantum numbers. For hydrogen, this has named some certain transitions are named. They're a series. So if our final destination, and again, this is going to be giving off energy, so we'll be coming from a higher energy state to a lower energy state. All the transitions down to n equals 1 form what is called the Lyman series. So here we have the final state k equals 1. Now j would have to be, j would have to be any value greater than 1, of course. And so 2 to 1, 3 to 1, 4 to 1, 5 to 1 form this series. Now, coming down to state 2 is called the Balmer series. And so here, this would be the final state of 2, j being any number greater than 2. Greater than 2, because we're coming down. Paschen series, and the final state being 3, and j would be greater than 3. There are other name series, so the final state being 4 is called the Brackett series. The final state being 5 is called the Fund series, and the final value being 6 is called the Humphrey series. After that, I don't think there's a name for these series. Okay. All right, well, this shows that the Bohr model is somewhat triumphant here. It's able to get some experimental results. Now, if you push it a little further, so if you put hydrogen in a really strong electric field, you get you don't get the results that match experiment. And likewise, if you put it in a very strong magnetic field. So there's these so-called fine structure and hyperfine structure splittings of these energies that you don't get with the Bohr model. So we know it's a step in the right direction, but it can't be right because we're still not getting everything right for hydrogen. And then the other thing, though, that is perhaps profoundly unsatisfying is why the heck these special orbits? I mean, what would make an orbit special, and what would make one not special? Well, this then points to one of the really core fundamental features of quantum mechanics. So there must be some kind of quantum behavior coming in, and the Bohr model is trying to capture that. And where it does is in these special orbits. And then, without understanding quantum mechanics at that time, then what do these special orbits mean? Well, it was starting to be understood that photons have a wavelength, but de Broglie showed that particles, you can think particles as having a wavelength. And so that idea coming in here, we say, okay, let's say an electron isn't like a planet or a little charged marble, but it's a wave. Okay, well, we can't see an electron, we can't pick it up and put it in our hand, so perhaps it's a wave and has a particular wavelength. Then we can look at the special orbits and say, there should be special orbits, because if I have hydrogen and it has a fixed wavelength, then I'm going to have to get an integer number of those waves to fit in that orbit. Otherwise, we won't create this standing wave in this orbit. So you can kind of imagine a brass ring, and if there's a fixed wavelength for the electron, we have to get an integer number of those on that brass ring in order to get to not have the waves interfere with each other and cancel each other out. And so if we have a particular radius here, r, that's not special, then we don't get standing wave formed. But if we have a special radius, we do. And in this particular case, here's one wavelength, here's another, 2, 3, 4, 5. So this would be the n equals 5 special radius, special orbit. And so that works. And so we say, okay, well, then I guess electrons are waves. But there were plenty of experiments at the time for electrons to indicate that electrons were behaving like particles. In fact, even the early experiments to figure out what an electron was, it was more a particle manifestation. And so then we have to take a step back and say, again, we can't pick this up like a marble or a baseball, what we have to sort of release our mind into thinking it has to be a particular thing like a particle or a wave. And so this helps us come to this, and other things help us come to the conclusion that an electron is neither a particle nor a wave, but has characteristics of both. This is called wave-particle duality. And a given experiment will pick out a wave-like or particle-like behavior of the electron. So that's the conclusion that one comes to with the Bohr model. And that's all of the further we're going to take things. You can do some additional calculations with the Bohr model, but there's no need to do that. We know that the Bohr model then was pretty quickly replaced by quantum mechanics. And the full-blown quantum mechanics for hydrogen was solved very quickly. And then between 1920 and 1926, when quantum mechanics was first published, in 1930, many of the chemical models were already solved. So things just really fell into place once quantum mechanics was developed. So next time we will look at the quantum mechanical solutions, right? We won't work through the solution, but we will look at the solutions for hydrogen. And this will give us a general chemistry, like a freshman general chemistry level understanding of atoms, which we will need to understand chemistry.